Okay, so skyscrapers. Every city's got them. Nobody really thinks about them. And honestly, they're kind of insane when you look into it. I'm gonna walk you through it tonight, nice and slow. No test at the end. Just close your eyes whenever. There is a building you have walked past 100 times without thinking about it. Maybe it is in your city. Maybe it is the one you can see from the window of a train, or the one that appears in the background of photographs you have taken on holidays in places you can barely remember now. It is tall, obviously tall. The kind of tall that makes you tilt your head back slightly when you are standing directly beneath it. The kind of tall that catches the last light of the evening, long after the streets below have gone dark and cool. You have probably never wondered how it got there. Not really. Not in the specific, physical, logistical sense of the word. You might have a vague impression of cranes and construction fences, of hard hats and concrete mixers, of noise and dust and the general inconvenience of something large being built in a city that is already full of large things. But the actual process, the sequence of events that turns a patch of ordinary urban ground into something that stands 400, 600, 1,000 feet in the air. That part tends to stay invisible, even to people who watch it happening every day. And the strange thing is, a remarkable portion of it happens at night. Tonight, while most of the city is asleep, somewhere in the world, a skyscraper is being built. The cranes are turning. The concrete is being mixed. Workers in high-visibility vests are checking pressure gauges and reading structural drawings by the light of temporary floodlights bolted to scaffolding that sways gently in the wind. The city carries on sleeping, and the skyline, very slowly, changes shape. This is the story of how that happens. Not the glamorous version. Not the version with time-lapse footage and dramatic music. The actual version. The one that begins not with steel and glass and cranes, but with something far more unglamorous and far more important. The ground. Before the first shovel. Here is something that surprises almost everyone when they first encounter it. For every year, a skyscraper is visible above ground. There is often a year, sometimes two, sometimes more, that you never see at all. A year spent in meetings. A year spent in laboratories. A year spent arguing about soil samples and zoning ordinances and the exact compressive strength of bedrock that no one living has ever seen, because it is buried 50 feet beneath a parking lot. Before a single shovel enters the ground on a major building project, an enormous amount of work has already been done, and almost none of it looks like construction. It begins, usually, with a question. Someone, a developer, a corporation, a city authority, decides that a particular piece of land should hold something tall. This is rarely a spontaneous decision. It follows years of real estate analysis, financial modeling, market studies, demographic projections, and the kind of slow institutional deliberation that produces dense documents that almost no one reads from cover to cover. The land is identified. The project is proposed. And then, before anything else, someone has to answer a question that sounds simple and is anything but. What is actually down there? The ground beneath a city is one of the most complicated things in the natural world. Cities tend to be built on geologically interesting ground: riverbeds, filled harbors, estuaries, former swamps, glacial deposits, Because throughout most of human history, people settled near water, and water tends to deposit exactly the kinds of soft, unpredictable soils that engineers find deeply uncomfortable. Manhattan is a narrow island of rock and glacial till. Chicago sits on ancient lake sediments and layers of soft clay left behind when Lake Michigan was much larger than it is today. Shanghai, one of the most aggressively skyscraper-dense cities on Earth, sits on a river delta, some of the softest, most compressible ground imaginable. Dubai, which has built some of the tallest buildings on Earth in an astonishingly short period of time, rests on a desert landscape where the rock underneath is surprisingly variable and the water table does unexpected things. Every one of these cities has found ways to build tall buildings on ground that, by strict geological standards, should probably not be holding up tall buildings at all. The process of understanding what is underneath a future building site is called a geotechnical investigation, and it is one of the least glamorous and most important steps in the entire construction process. Teams of engineers arrive on the site before any demolition has occurred, before the design has been finalized, sometimes before the building has even been fully conceived, and they begin drilling. Not constructing, drilling. Small, precise holes, often dozens of them, bored down through the existing pavement and soil to retrieve samples from depths that the building will eventually need to understand. These cores of material, cylinders of compressed earth, cooled clay, gravel, sand, and sometimes rock, get sent to laboratories where geotechnical engineers study them with a patience and attention to detail that borders on the obsessive. They test the bearing capacity of the soil, meaning its ability to hold weight without compressing or shifting. They measure water content, the angle of internal friction, the consolidation characteristics under load. They look for layers of soft material that might compress unpredictably over decades, causing the building above to settle unevenly. They look for voids, for buried structures, for old contamination from industrial uses, for the remnants of whatever was on this land before the city covered it up. And cities have covered up a great deal. There are skyscraper sites in London where geotechnical investigations have uncovered Roman artifacts buried 20 feet down. Sites in New York where the drill cores have passed through the wooden pilings of 18th century wharves, the remnants of the waterfront that used to exist before Manhattan's edges were extended outward with landfill. Sites in Asian cities where ancient wells, old riverbanks, and the foundations of buildings that have not existed for centuries are still present underground, still capable of complicating the behavior of a foundation that will need to carry millions of pounds. The geotechnical report that results from all of this investigation is a dense technical document that most people on a construction project never read in full. But it shapes everything. The type of foundation, the depth of the basement, the cost of the project, sometimes the feasibility of the project at all. There have been sites where geotechnical investigations revealed conditions so different from what was expected that projects were canceled, relocated, or fundamentally redesigned before a single piece of equipment had been moved into position. The ground has a way of making its own decisions, regardless of what appears on the architectural drawings. And this is before the planning process has even properly begun. The permits, the politics, and the years of waiting. The phrase building permit tends to conjure something bureaucratic and minor. A form submitted, a fee paid, a stamp applied. For a skyscraper, the reality is so far from this that the phrase barely applies. Getting permission to build a tall building in a major city is one of the most complex regulatory processes in the modern world. It involves multiple government agencies at multiple levels. It involves environmental impact assessments that examine everything from the building's shadow on neighboring parks to its effect on local wind patterns at street level. It involves public comment periods, community board hearings, appeals, counter-appeals, and an almost inexhaustible supply of legal challenges from neighbors, preservationists, rival developers, local politicians, and occasionally activist groups with concerns ranging from the entirely reasonable to the deeply idiosyncratic. In New York City, the approval process for a major skyscraper can involve the Department of Buildings, the Board of Standards and Appeals, the Landmarks Preservation Commission. If the site is near a historic building, the City Planning Commission, the environmental review process under the State Environmental Quality Review Act, the Federal Aviation Administration for buildings that might affect flight paths, and sometimes additional federal agencies depending on the nature of the site. Each of these entities has its own timeline, its own requirements, its own staff of reviewers, and its own capacity for generating delays. In London, a building above a certain height in certain zones must receive approval not just from the local authority, but from the Mayor of London's office, which evaluates the project against the city's strategic planning policies, including assessments of protected view corridors, lines of sight to landmarks like St. Paul's Cathedral that have been legally protected for decades. In Tokyo, earthquake risk requirements are so stringent that structural engineering review is essentially its own parallel approval process, conducted simultaneously with architectural review and often extending the overall timeline significantly. This is not a criticism of these processes. Many of them exist for very good reasons, and the history of urban development is full of examples of buildings that would have benefited from more scrutiny rather than less. But it is worth understanding that by the time a large skyscraper project finally receives all of its necessary approvals and is ready to begin construction, the team that started the process may have been working on it for 5, 7, 10 years. The architects may have produced multiple design iterations that were rejected or substantially revised in response to regulatory feedback. The developer may have assembled and reassembled the project's financing several times as market conditions changed. The building that eventually gets built is often considerably different from the building that was first imagined. There is a skyscraper in London called the Shard, the tall, glass-spired tower that now dominates the South Bank skyline, whose planning approval process was so contentious that it required a public inquiry chaired by a government-appointed inspector and ultimately had to be decided by the Deputy Prime Minister personally. The building was first proposed in 2000. Construction did not begin until 2009. It was completed in 2012. 12 years from concept to completion, and the physical act of building it took only 3. That ratio, 3 years of construction against 9 years of everything else, is not unusual. It is closer to typical. The demolition that comes first. One more thing happens before the first foundation work begins, and it is a stage of the process that gets very little attention despite being genuinely fascinating in its own right. Something usually has to be removed. Major skyscrapers in established cities are almost never built on empty land. They are built on sites that previously contained other buildings, older commercial structures, industrial buildings, car parks, sometimes entire city blocks of mixed-use buildings that have been acquired one by one over years through processes that involve their own negotiations, their own delays, and their own particular complications. Demolition in a dense urban environment is not simply a matter of knocking things down. It is a carefully sequenced process that has to consider the structural conditions of neighboring buildings that share walls or foundations, the presence of underground utilities that cannot be disrupted, the management of dust and debris in areas where thousands of people are walking, working, and living within 100 feet of the demolition zone. Before any demolition begins, utility companies must be contacted to identify and reroute or protect water mains, gas lines, electrical conduits, telecommunications cables, and, in older cities, the occasional mystery pipe of unknown origin and unclear purpose that appears in records from the 1920s and has been quietly doing something unspecified ever since. Environmental remediation is often required before demolition can proceed. Many urban sites contain contamination from previous industrial uses, petroleum products, heavy metals, asbestos in older building materials. The presence of asbestos in a building scheduled for demolition triggers an entirely separate regulatory and logistical process, because asbestos removal must be carried out by specially licensed contractors under controlled conditions before any other demolition work can begin. The demolition itself, once it starts, tends to proceed in a direction that surprises people who are not familiar with the process. Rather than collapsing a building from the outside in, as the popular image of demolition tends to suggest, most urban demolition works from the top down. Buildings in dense cities are taken apart floor by floor, often using excavators mounted on platforms at upper levels, with the debris carefully managed and brought down by chute or by controlled internal processes rather than simply dropped onto the street below. The whole thing is slower, more careful, and more expensive than most people imagine. And by the time the site is cleared, the project has already spent a significant portion of its budget without a single piece of the new building having been created. The hole that swallows city blocks. Now the ground opens up. Excavation for a major skyscraper is one of those processes that is difficult to truly appreciate until you have stood at the edge of one and looked down. The basement of a tall building in a city is not a modest space. It is several floors of structure below ground level, often 3, 4, sometimes 6 or more basement levels, that will eventually contain parking, mechanical equipment, electrical infrastructure, loading docks, storage, and the upper portions of the foundation system. The pit required to create this space is enormous for a mid-sized skyscraper in a city like New York, Chicago, or Hong Kong. Excavation might require the removal of somewhere between 500,000 and several million cubic feet of earth and rock. This material has to be moved. It has to be loaded into trucks, driven through city streets, and deposited somewhere, either at landfill sites or, if the excavated material is clean enough and the right consistency, sold to other construction projects that need fill. Moving this volume of material through a functioning city creates a logistical challenge that the construction team has to solve before the first excavator enters the pit. The trucks that haul excavated material cannot simply drive through city streets at all hours. There are noise regulations, weight limits on certain roads, restrictions on truck movements near schools and hospitals during certain times of day. Routing plans have to be developed, approved by city transportation authorities, and coordinated with the construction schedule. The number of truck movements per day and the specific hours during which they can occur is often negotiated with the local community as part of the approval process. On a large excavation project, the truck traffic generated by earth removal can be extraordinary. Hundreds of truck movements per day, sustained over months. Each truck represents a planning decision: the route, the timing, the weight of the load, the location of the tipping site, that has to mesh with thousands of other decisions being made simultaneously on and around the construction site. And this is before the question of the pit's walls. When you dig a large hole in a city, the ground around the hole has a natural tendency to want to slide into it. This is not a theoretical concern. It is a physical reality governed by soil mechanics, and the consequences of getting it wrong range from expensive to catastrophic. If the sides of a deep urban excavation fail, they can damage or destroy neighboring buildings, rupture underground utilities, and create collapses that endanger everyone in the vicinity. The engineering of what is called earth retention, the system of structures that holds the walls of the excavation in place while it is open, is one of the most technically demanding aspects of early skyscraper construction. There are several different approaches, and the choice between them depends on the soil conditions, the depth of the excavation, the proximity of neighboring structures, and the specific constraints of the site. Slurry walls and the art of digging carefully. One of the most common and elegant solutions to the earth retention problem in dense urban excavations is a structure called a slurry wall, or sometimes a diaphragm wall. The name comes from the material used to create it, and the method by which it is built is, once you understand it, quite extraordinary. Here is the basic idea. Before any general excavation begins, a narrow trench is dug around the perimeter of the site, the footprint of where the pit's walls will eventually be. This trench is dug in sections, each one perhaps 20 to 30 feet long and only a few feet wide, but potentially 60, 80, or even 100 feet deep, depending on the requirements of the foundation. As the trench section is excavated, it is immediately filled with a slurry, a mixture of water and a mineral called bentonite, which has the remarkable property of naturally forming a thin, nearly impermeable filter cake against the walls of the trench. This bentonite slurry exerts pressure against the trench walls that prevents them from collapsing inward while the trench is open. Into the slurry-filled trench, a steel reinforcing cage is lowered, a prefabricated structure of reinforcing bars that will give the eventual concrete wall its tensile strength. Then concrete is pumped into the bottom of the trench through a special pipe called a tremai. And as the concrete rises, it displaces the bentonite slurry upward, which is pumped away and collected for reuse. The result, when the concrete sets, is a continuous concrete wall around the perimeter of the site that was constructed entirely from the surface downward, without any general excavation having occurred yet. This wall simultaneously serves as the earth retention structure during excavation and as the permanent below-grade wall of the finished building's basement. In a dense urban environment, where the margins between the construction site and neighboring buildings can be measured in feet rather than yards, this approach allows deep excavations to proceed with a degree of control and safety that would have been impossible with earlier methods. There are other approaches: soldier piles and lagging, sheet pile walls, soil nailing, each appropriate to different soil conditions and different depths. But the slurry wall represents a kind of quiet triumph of applied engineering in a field that most people never hear about, solving a problem of extraordinary physical complexity with an approach that is almost deceptively simple in its basic logic. The excavation itself, once the perimeter is secured, proceeds inward and downward in a carefully planned sequence, with temporary horizontal bracing added as the dig gets deeper, counteracting the lateral pressure of the earth outside the wall. On some large projects, The excavation and the construction of the lower basement structure proceed simultaneously in a method called top-down construction, where the ground floor of the building is constructed first and the excavation continues downward beneath it, using the finished structure above as the bracing system. This approach is particularly useful in city centers, where the ground floor needs to be returned to use as quickly as possible, or where surface settlements have to be minimized to protect neighboring buildings. All of this, the slurry walls, the bracing, the sequenced excavation, the dewatering systems that pump groundwater out of the pit as it accumulates, is happening before any of the permanent above-grade structure has begun. Months of work, hundreds of workers, enormous quantities of material, significant cost, and nothing yet visible from the street except a fence, a gate, and a sign with an architect's rendering of what will eventually stand here. What holds it all up? The foundation of a tall building is the part of the structure that most fundamentally determines everything else. It is the interface between the engineered structure and the natural world, the place where the immense forces generated by a building's weight, by the wind loading on its upper floors, by the vibrations of the city around it, are transferred into the earth below. Getting this wrong is not an option. The foundation is the one part of a skyscraper that cannot be accessed, inspected, or repaired once the building is complete. Whatever is down there when the concrete sets is what will be down there forever. The most fundamental question in foundation engineering is where the loads are going. The weight of a tall building, and we are talking about forces measured in tens of millions of pounds for a significant skyscraper, has to be transferred somewhere stable. Ideally, it goes into bedrock, the solid underlying geology that does not compress under load. But bedrock is not always conveniently located at a depth that makes direct contact practical. In Manhattan, bedrock is relatively close to the surface in some areas and much deeper in others, which is one reason why the famous clusters of skyscrapers in Lower Manhattan and Midtown exist where they do, rather than in the areas between them, where the bedrock drops away to depths that were, historically, more expensive and difficult to reach. This geological reality shaped the skyline of New York City in a way that most people who love that skyline have never considered. In cities like Chicago, Houston, or Shanghai, bedrock may be so deep that reaching it directly is impractical, and foundation engineering has to work with the soils available, using strategies that spread the load over a large enough area or transfer it down through soft upper layers to denser material below. Piles, caissons, and the deep logic of foundation engineering. The most common approach to deep foundation work for tall buildings involves some form of deep foundation element, either driven piles or drilled shafts, which are sometimes called caissons or drilled piers, depending on the specific method and the regional engineering tradition. Driven piles are exactly what they sound like. Long structural elements, steel H-piles, steel pipe piles, or precast concrete piles, are driven into the ground using a pile driver, a machine that delivers repeated hammer blows to the top of the pile, forcing it downward through the soil until it either reaches the target depth or develops sufficient resistance from the surrounding soil and underlying material. The resistance that a pile develops over its length, from friction with the surrounding soil, combined with the bearing resistance at its tip, is what allows it to carry vertical load. Pile driving is one of the louder phases of any construction project, and in an urban environment, it is also one of the more diplomatically challenging. The percussive impact of a pile driver carries through the ground as vibration, which can be felt in neighboring buildings, and, if the soil conditions are right, at considerable distances from the site. Managing this requires careful monitoring of vibration levels in adjacent structures, particularly older masonry buildings that can be more vulnerable to settlement or cracking from repeated ground vibrations. Drilled shafts work differently. Rather than driving an element into the ground, the drilled shaft method involves boring a hole into the earth using a large rotary drilling machine, sometimes several feet in diameter and potentially 100 feet or more in depth, and then filling that hole with a reinforced concrete column. The borehole might be drilled through soft soils and into rock, where the base of the shaft is sometimes further enlarged using a special tool that creates a bell-shaped cavity, a bell caisson, which dramatically increases the bearing area at the base and therefore the load-carrying capacity of the element. For a major skyscraper, the foundation system might consist of dozens or hundreds of individual piles or drilled shafts, each one carefully positioned to receive the loads from specific columns or walls above, each one designed to carry a precisely calculated load to the bearing strata below. The structural engineering of the foundation is as complex and carefully considered as any other part of the building. The mat foundation. On some sites, particularly those where the soil is relatively uniform and the building's footprint is large relative to its height, a different approach is used. Instead of individual piles or shafts, the entire base of the building is supported on a single enormous concrete slab, a mat foundation, sometimes called a raft foundation, that essentially floats the building on the soil the way a raft floats on water, spreading the building's weight over the largest possible area. Mat foundations for major buildings are remarkable structures. They are typically several feet thick. On large buildings, mat foundations of 8, 10, or 12 feet of solid reinforced concrete are not uncommon, and they contain enormous quantities of steel, reinforcing, and concrete. They also generate an engineering challenge that relates directly to the concrete itself. Concrete, as it sets, undergoes a chemical reaction that produces heat. This is fine in small quantities, but in a very large concrete pour, the sheer volume of concrete means that the heat generated by the setting reaction in the interior of the pour cannot escape to the surface quickly enough, and temperature differentials develop between the hot interior and the cooler surface and edges. If these temperature differentials become large enough, they can cause cracking, and cracking in a foundation mat is not something anyone wants to discover. Managing the heat of a massive concrete pour is a genuine engineering challenge. In hot weather, the ingredients of the concrete mix might be chilled before batching. Ice is sometimes added to the mixing water. Temperature sensors are embedded in the concrete so that the heat development can be monitored in real time. Insulating blankets may be applied to the surface to slow the rate of cooling there, reducing the differential between the interior and the exterior. On very large foundation pours, pipes carrying cool water may be embedded in the concrete to actively remove heat, a process called internal cooling. And this is what sets the context for one of the most striking facts about large skyscraper foundations: the continuous pour. The concrete that never stops foundation. Concrete pours for major skyscrapers are among the largest single concrete placements in the construction industry. For a large mat foundation, the volume of concrete required might be measured in thousands of cubic yards, a quantity that represents hundreds or even thousands of individual concrete truckloads. The reason this concrete must be placed continuously is a property of concrete called the cold joint. When fresh concrete is placed against concrete that has already begun to set, the interface between them, the cold joint, represents a plane of weakness in the finished structure. In a foundation mat that is designed as a monolithic structural element, cold joints are not acceptable. The entire mat must be poured as a single continuous operation, without allowing any portion to begin its initial set before the adjacent concrete is placed. For a large foundation pour, this means that the concrete must keep arriving, keep being placed, and keep being consolidated, using vibrators that are pushed into the concrete mix to eliminate air pockets, 24 hours a day without interruption until the pour is complete. These pours can take 30, 40, 60 hours or more. The planning required to sustain this uninterrupted operation is extraordinary. Concrete plants have to be identified within a reasonable hauling distance of the site, and their combined batching capacity has to be sufficient to keep the placement rate on schedule. Multiple plants are typically used, so that if one plant has a mechanical problem, the pour can continue from the others while repairs are made. Truck routes are planned and timed, so that there is a continuous queue of loaded trucks arriving at the site, while empty trucks return for their next load. Pumps, large truck-mounted or stationary concrete pumps with booms that can reach across the excavation, are positioned to distribute the concrete to all parts of the pour. Backup pumps are on standby in case of mechanical failure, and all of this happens around the clock. The trucks roll through the empty city streets at 3 in the morning. The pump operators stand at their machines as the temperature drops and the night deepens. The concrete finishers work by floodlight, consolidating and leveling the surface of the rising mat, while the next truck backs into position behind them. This is what it looks like when the most fundamental structural element of a skyscraper is being created. Not glamorous, not dramatic, just continuous, careful, highly coordinated physical work, sustained through the night, long after the city above has gone to sleep. Water, rock, and the ground's own agenda. Even the most careful geotechnical investigation does not always anticipate everything that the ground will do once work begins. Groundwater is a persistent complication on almost every urban excavation. Cities are threaded with water, the remnants of natural drainage systems, the leakage from decades of aging water mains, the infiltration from rain and snowmelt that percolates down through the soil. When a deep pit is dug in this environment, water migrates toward it from all directions, finding paths through the soil that no survey could fully predict. Dewatering, the process of removing this infiltrating groundwater from the excavation to keep the pit dry enough to work in, is an ongoing operation throughout the foundation phase of construction. It involves a network of pumps and wells around and within the excavation, continuously operating, drawing the water table down around the site. The water that is pumped out has to go somewhere, typically into the city stormwater system, after passing through settling tanks to remove any suspended sediment. Dewatering at scale creates a secondary concern that is sometimes overlooked. Lowering the water table around a site reduces the water pressure in the soil in the surrounding area. In soils that contain organic material, particularly old-filled land with wood or peat components, reducing the water content can cause consolidation. The soil compresses as the water that was supporting its structure is removed. This consolidation manifests at the surface as settlement. The ground subsides, sometimes by fractions of an inch, sometimes by more. In a dense urban environment, even small settlements can cause damage to neighboring buildings, and monitoring systems, precise survey monuments attached to adjacent buildings, read at regular intervals by survey teams, are maintained throughout the dewatering operation to detect any movement before it becomes a problem. Rock presents its own category of challenges. When the drill hits bedrock, it might seem like the hard part is over. Bedrock is strong, stable, and predictable. But bedrock in cities is rarely a smooth, uniform surface. It undulates. It has joints and fractures. It sometimes contains cavities, either natural or the result of historical mining or quarrying operations. Different parts of the same building's footprint may encounter bedrock at very different depths, meaning that some foundation elements need to be much longer than others to reach the same bearing stratum. In some cities, the rock is so hard that drilling through it for foundation shafts requires specialized equipment and proceeds at rates measured in feet per hour rather than feet per day. Diamond-tipped core drilling is sometimes used in particularly hard formations. Controlled blasting may be required to break up rock that is too hard and too thick for mechanical drilling alone. An operation that, in a dense urban environment, requires extraordinary coordination, including precise calculation of blast charges, notification of neighboring buildings and utilities, and monitoring of vibration and air pressure effects. There are foundation projects where the ground revealed surprises that were genuinely extraordinary. In parts of Lower Manhattan, excavations have encountered the stone rubble used to create the landfill that extended the island's shoreline in the 17th and 18th centuries, a layer of historical material as unpredictable as any natural deposit. In London, foundation work in the city center has encountered the remnants of the Roman city wall, requiring archaeological recording and sometimes selective preservation before construction could continue. In Hong Kong, the hard granite bedrock that makes the city's foundations geologically simpler in some ways also presents extraordinary challenges to drill through, demanding equipment and expertise that has made Hong Kong's geotechnical contracting industry among the most technically accomplished in the world. The ground, in every city, has its own character. The engineers who work with it develop a kind of expertise that is partly technical and partly intuitive, an understanding not just of the numbers in the geotechnical report, but of how particular soils and rocks behave when disturbed, what they tend to do that is not in the report, and how to respond when they do something unexpected. This is the knowledge that gets a skyscraper started. Not the architecture, not the steel, not the glass. The ground. The careful, unglamorous, absolutely essential understanding of what is down there, what it will do when you disturb it, and how to build something permanent on top of something that has its own slow geological agenda. By the time the foundation work is complete, the walls built, the excavation finished, the mat poured, or the piles installed, the basement structure beginning to take shape, an enormous amount has happened that no one passing by the site would ever be able to see or appreciate. Hundreds of thousands of dollars, sometimes millions, hundreds of workers, months of continuous effort. And the result is something almost entirely underground, invisible, undramatic, the opposite of the gleaming tower that the architectural rendering promised. But it is the most important thing that will ever happen on this site. Because everything that comes next, every floor, every column, every ton of steel and glass and concrete that will eventually constitute one of the most visible structures for miles around, rests entirely on what happens beneath the surface. Quite literally, the skyscraper begins in the dark. Tonight, in some city in the world, The concrete is still being poured. The pump is still running. The trucks are still arriving, their headlights sweeping across the chain-link fence at the site entrance. The driver climbing down from the cab in the pre-dawn cold. The poor supervisor checking his clipboard and nodding. And the city above still sleeping, entirely unaware that something enormous is quietly, carefully, irreversibly beginning. There is a moment in the construction of every skyscraper that is difficult to describe unless you have witnessed it. It happens sometime after the foundation work is complete, after the basement levels have been formed and the lowest structural columns have been set, after all the invisible underground work has been done and the site has been quiet in that particular way that major construction sites go quiet between phases. When the machinery of one operation has finished and the machinery of the next has not yet fully arrived. And then the steel starts coming. It does not arrive all at once. It could not. The fabricated structural steel for a major skyscraper would, if assembled in one place at one time, constitute an almost incomprehensible quantity of material. So it arrives in a sequence, a carefully planned, precisely timed sequence that represents one of the more remarkable feats of logistics in the entire construction process. A truck arrives at the gate. On its flatbed, wrapped in protective coating and marked with codes that correspond to specific positions on the structural drawings, are pieces of steel that were fabricated in a factory that may be hundreds or thousands of miles away, cut and drilled and welded to tolerances measured in fractions of an inch, designed to fit together in a specific configuration, at a specific elevation, on a specific day. The ironworkers are waiting. The steel that arrives from somewhere else, the structural steel in a major skyscraper, begins its life far from the building site. It begins, in most cases, at a steel mill, a facility where iron ore and recycled scrap steel are processed in electric arc furnaces at temperatures above 3,000 degrees Fahrenheit into the basic shapes that structural engineering depends on. Wide flange beams, hollow structural sections, heavy columns, plate steel. These basic shapes emerge from the rolling mills in standard lengths and standard dimensions, and are then shipped to structural steel fabricators, specialized industrial facilities that take these standard shapes and transform them into the precise, custom-cut, pre-drilled, sometimes pre-welded components that a specific building requires. Structural steel fabrication is a manufacturing process of considerable precision. The fabricator works from detailed shop drawings, engineering documents that translate the architect's and structural engineer's design intent into exact dimensions, connection details, and assembly sequences for every piece of steel in the building. A large skyscraper might contain thousands of individual steel pieces, each one different, each one requiring its own set of fabrication operations. Computer numerical control equipment, CNC machines that are essentially very large and very precise automated cutting and drilling tools, handle much of the dimensional work. A wide flange beam arrives at the fabrication shop in a standard length. The CNC equipment cuts it to the exact length required for its position in the structure, drills the bolt holes in the precise pattern required for the connections at each end, and sometimes cuts cope notches, small rectangular cutouts at the corners of the beam web that allow the beam to fit tightly against an adjacent column without interference. Welding is performed by certified welding technicians who are qualified to specific standards depending on the type of weld and the criticality of the joint. Not all welding in a steel structure is the same. Some connections are made in the shop under controlled conditions and inspected before the piece leaves the factory, while others are field connections made on the building site, and still others are hybrid connections where some welding is done in the shop and completed in the field. The American Institute of Steel Construction maintains codes and standards that govern all of this, and structural steel fabrication shops are regularly certified against these standards. After fabrication, the steel pieces are typically cleaned and given a primer coat of paint or other surface treatment to protect them from corrosion during transportation and storage. They are then marked with identifying codes, often painted directly on the steel using stencils, that correspond to their position in the erection sequence. And then they wait, either in the fabricator's yard or in a staging yard near the construction site, for their moment to be called. The sequencing of steel delivery to a construction site is a discipline unto itself. The site has no storage space. It is an active construction zone in the middle of a city, and every square foot of the site is spoken for. Steel cannot arrive before it is needed, because there is nowhere to put it. But it also cannot arrive late, because the ironworkers and the crane are waiting, and idle ironworkers and a standing crane are expensive. The steel has to arrive at the site in exactly the sequence in which it will be erected, at approximately the time when the erection crew is ready for it. This requires detailed coordination between the erection contractor, the fabricator, the trucking companies, and the site logistics team, sustained over months as the structure rises. It is the kind of coordination that is largely invisible to anyone watching from the outside, but represents an enormous amount of careful planning and real-time problem-solving by the people managing it. The ironworkers. The people who actually assemble the steel structure of a tall building belong to one of the most distinctive trades in the construction industry. Structural ironworkers, members of the International Association of Bridge, Structural, Ornamental, and Reinforcing Ironworkers, have a culture and a professional identity that is unlike anything else in the building trades, shaped by the particular demands, dangers, and satisfactions of work that literally takes place in the open sky. The trade has a long history. The late 19th century, when steel frame construction was first being developed in Chicago and New York, saw the emergence of a class of workers who specialized in the dangerous business of assembling iron and steel structures at height. Many of the most celebrated early ironworkers were Mohawk men from the Kanawake community near Montreal, whose involvement in structural steelwork began with the construction of the Victoria Bridge across the St. Lawrence River in the 1880s, and who went on to become a significant presence in the high steel industry of New York City and other northeastern cities throughout the 20th century. The Mohawk ironworkers of Kanawake were observed by early writers and journalists to display an unusual ease with heights that was often attributed to some inherent cultural characteristic. This interpretation was more romantic than accurate. The more likely explanation is simply that ironwork became an established trade within the community, transmitted from fathers and uncles to sons and nephews over generations. And that familiarity with the work from childhood, combined with proper training and mutual support within a close-knit working group, produced workers who were highly competent and consequently appropriately confident at heights where untrained workers would be paralyzed. The trade remains demanding. Modern ironworkers are required to complete apprenticeship programs that combine classroom instruction in the theory of structural connections, rigging, and safety with extensive on-the-job training under the supervision of journeymen and foremen. They must be physically capable. The work involves carrying heavy tools, navigating uneven and sometimes slippery steel surfaces, operating in weather conditions that range from summer heat to winter cold. and maintaining concentration and coordination in an environment where the consequences of a lapse in attention are severe. The specific work of erecting a structural steel frame involves several distinct roles. Connectors are the workers who physically handle the steel as it comes off the crane. They guide each piece into position, align it with the existing structure, and drive the first bolts to make the initial connection. This work is done at the leading edge of the structure, often the highest and most exposed position on the entire building, with nothing below but open air and the construction site several hundred feet down. Bolters follow behind the connectors, installing the permanent bolts and tightening them to the specified torque. Tagline operators on the ground or on lower floors manage the rope lines attached to the swinging steel to control its movement as the crane brings it up. The connector team at the top of the structure has to communicate constantly with the crane operator, often through hand signals when radio communication is interrupted by noise or distance, to coordinate the placement of each piece with the precision that structural work demands. Walking the iron, as the ironworkers call it, moving across the exposed structural frame at height on beams that may be only 6 or 8 inches wide, with open air on both sides, is something that simply has to be experienced in the trade. Modern safety regulations require fall protection, harnesses, lanyards, safety cables, in most situations, and the implementation of these requirements has substantially reduced the frequency of fatal falls compared to earlier eras when ironworkers routinely worked on exposed steel with no fall protection whatsoever. But the fundamental nature of the work, the exposure to height, the physical demands, the requirement for precise and coordinated action in a dynamic and unpredictable environment, remains essentially unchanged from the era when the first skyscrapers were being assembled piece by piece against the sky. How a skyscraper grows. The structural logic of a tall building is one of those things that seems obvious in retrospect, but took decades of engineering development to work out in practice. The earliest tall buildings, the pioneering iron and steel frame structures built in Chicago in the 1880s and 1890s by architects like William LeBaron Jenney, Louis Sullivan, and Burnham and Root, used a structural approach that was essentially a rigid three-dimensional cage of iron or steel columns and beams. The frame carried all the loads, vertical gravity loads from the weight of the building, and lateral loads from wind, through the stiffness of the connections between the frame members. This worked well enough for buildings of 10, 15, 20 stories. But as buildings got taller, the efficiency of this approach decreased. More and more of the building's structural capacity had to be devoted to resisting wind, leaving less available to support the building's own weight and occupants. The structural innovation that made true skyscrapers possible was the separation of structural functions, assigning the gravity loads and the lateral loads to different structural systems that each did their job more efficiently than a single rigid frame could do both. The modern approach to tall building structure, developed through the mid-20th century and refined ever since, typically involves a central concrete core combined with a perimeter structural system of some kind. The core, a thick-walled concrete tube or box that runs the full height of the building, housing the elevators, stairs, mechanical shafts, and restrooms, is enormously stiff and strong, and carries a significant portion of the lateral load from wind and in seismic zones from earthquakes. The perimeter structure, columns and beams, or, in some designs, a diagonal bracing system or a perforated tube, carries gravity loads and contributes additional lateral stiffness. The interaction between the core and the perimeter structure is the heart of tall building structural engineering. Different buildings handle this relationship differently, and the specific solution chosen for any particular building depends on its height, its aspect ratio, the relationship between its height and its width, the local wind and seismic environment, the construction budget, and the aesthetic requirements of the architectural design. The concrete core has a particular construction logic that is worth understanding, because it largely determines the rhythm of the entire building's construction. The core is almost always built ahead of the steel frame. It rises floor by floor using a specialized formwork system that allows the concrete to be poured in lifts, with the formwork being stripped, raised, and reset for the next pour. This process is called slip forming or jump forming, depending on the specific technique, and it allows the core to advance several floors ahead of the steel frame that is being erected around and attached to it. This separation is intentional. Having the core several floors ahead of the steel erection means that the structural connections between the core and the steel frame are always being made to concrete that has had sufficient time to reach adequate strength. It also means that the elevator shafts and stair shafts inside the core are progressing ahead of the floor construction, which has implications for the installation of the elevators themselves, a process that begins long before the building is complete and proceeds from the bottom up as the shafts become available. The tower crane. It is impossible to tell the story of skyscraper construction without spending time on the machine that makes most of it possible. The tower crane is one of the defining objects of modern urban construction, visible from miles away, its horizontal jib swinging slowly against the sky, its hook tracing invisible arcs through the air above the building site. Most people have looked at one without giving it much thought. They probably should give it more. A tower crane is, in basic terms, a rotating crane mounted on a tall vertical mast. The horizontal arm, the jib, extends in two directions from the top of the mast, a longer load-carrying jib in one direction, along which a trolley moves to position the hook at different radial distances from the mast, and a shorter counter jib in the opposite direction, which carries the counterweights that balance the load on the hook. The crane rotates on a slewing ring at the top of the mast, allowing it to cover a full 360-degree working radius. The basic concept is not complicated. The execution is remarkable. A large tower crane can lift loads of several tons to heights of several hundred feet with a precision that, to anyone watching from the ground, seems almost impossible. The crane operator sits in a cab near the top of the mast, a small enclosed space with excellent visibility in all directions, but no direct view of the hook or the load below the jib, and controls the crane through a combination of cameras, radio communication with the rigging crew, and connectors on the structure below, and years of experience that have developed an intuitive feel for the dynamics of loads suspended on long cables. What makes the tower crane genuinely extraordinary is the question of how it gets there in the first place, and how it gets taller as the building grows. A tower crane arrives at the construction site in sections, transported on flatbed trucks. The mast sections, typically about 20 feet in height each, are assembled on the ground and erected using a mobile crane that is itself brought to the site for the purpose. Once the tower crane is assembled to an initial working height, the mobile crane departs, and the tower crane begins its work. As the building rises past the tower crane's working height, the crane must grow too. This is accomplished through a process called climbing, and it is one of the more counterintuitive operations in all of construction. The top section of the crane, the slewing unit, the cab, the jib, and the counter jib is temporarily jacked upward using a hydraulic climbing frame that fits around the outside of the mast. As the top of the crane is raised, a gap opens in the mast below it, and a new mast section is swung into the gap and bolted in place. The hydraulic frame releases, the top of the crane settles onto the new mast section, and the crane is now one section taller. This process, which takes a skilled crew several hours and involves lifting and installing pieces of steel, while the crane is essentially in a partially disassembled state, is performed at whatever height the crane has reached, which, on a tall building, might be several hundred feet in the air. Some tower cranes used on very tall buildings are not freestanding at all. They are tied to the building structure itself at multiple points up their height, with the building providing lateral support to the crane mast. As the building rises and the crane climbs, new ties are installed above and old ones below may be removed. The crane and the building grow together in a structural partnership, each temporarily dependent on the other. At the end of construction, the crane must come down. This is accomplished in the reverse of the climbing process, with mast sections removed one at a time as the top of the crane descends. Eventually, the crane is at a height that can be reached by a mobile crane brought back to the site, and the final disassembly takes place from the ground up. On buildings so tall that no mobile crane can reach their upper floors, the tower crane is sometimes disassembled in pieces small enough to be carried down through the building's interior in the elevators. That last detail, the tower crane eventually departing through the elevators it helped to build, is one of those facts about construction that is so improbable sounding that it deserves a moment's appreciation. Curtain walls and the skin of glass. Once the structural frame has risen to a sufficient height and the floor slabs have been completed, another trade takes over the exterior of the building. The glaziers, the curtain wall installers, the cladding workers, the people who give the skyscraper its skin. The exterior walls of a modern skyscraper are almost never load-bearing. They carry no structural load from the building. That job is done by the columns and the core. Instead, the exterior wall system hangs from or attaches to the structural frame, forming what is called a curtain wall, a non-structural enclosure that keeps the weather out, admits light, and gives the building its visual character. This distinction, the separation between structure and skin, was one of the defining innovations of modern architecture. In traditional masonry construction, the walls were the structure. They had to be thick and heavy to carry the building's weight, which limited how large the windows could be and how tall the building could go before the walls at the base became impossibly thick. The steel frame liberated the exterior wall from structural responsibility, allowing the skin of the building to be as transparent or as thin as the architect chose, independent of structural requirements. Modern curtain wall systems are far more complex than their apparent simplicity suggests. A glass curtain wall is not simply glass panels held in frames. It is an engineered system of aluminum or steel extrusions, structural silicone sealants, gaskets, thermal breaks, drainage channels, and glass units that may themselves be layered assemblies of 2 or 3 panes of glass, with specialized coatings and gas-filled cavities between them. The glass units in a modern high-performance curtain wall are typically insulating glass units, 2 or 3 panes of glass sealed together at the edges with a hermetically sealed cavity between them, often filled with argon or krypton gas, which is a better insulator than air. The glass itself may be coated with thin metallic films, low emissivity coatings, that allow visible light to pass through while reflecting infrared radiation, reducing the amount of solar heat that enters the building in summer and the amount of interior heat that escapes in winter. The specific combination of glass thicknesses, coatings, cavity fills, and frame systems is engineered for each building to achieve target performance values for thermal insulation, solar heat gain, visible light transmission, and acoustic performance. And all of this has to work in a building that moves. A tall building is not a rigid structure. It flexes in the wind, settles slightly under load over time, expands and contracts with temperature changes across an enormous range. A steel frame building in a climate with significant temperature variation might experience overall height changes of several inches between the coldest winter day and the hottest summer day, and lateral movements at the upper floors in a strong wind that can be measured in feet. The curtain wall system has to accommodate all of this movement without leaking, without cracking its glass, and without losing the airtight and watertight integrity of its seals. This is achieved through a system of designed movement joints, gaps and overlaps in the curtain wall assembly that are intentionally sized to allow relative movement between adjacent panels while maintaining continuity of the weather barrier. The engineering of these movement joints and the selection and testing of the sealant materials that must remain flexible and adhesive over decades of repeated cycling is a specialized discipline that requires careful analysis of the structural movements the building will experience, the thermal movements of the cladding materials, and the compatibility of all the materials in the assembly. Before any curtain wall system is installed on a building, it is subjected to extensive laboratory testing. Mock-up panels, full-size sections of the proposed curtain wall system, are constructed and installed in specialized test chambers, where they are subjected to simulated wind pressure, water penetration testing under simultaneous wind load, seismic racking tests that simulate the drift of a structural frame, and thermal cycling through the temperature range the building will experience in service. Only after the system passes all of these tests does the production installation begin. The installation of a curtain wall on a tall building is a slow, methodical, floor-by-floor operation. Panels arrive at the site by truck, are lifted by the tower crane, or by specialized hoisting equipment mounted on the facade itself, and are installed by small teams of glaziers working from scaffolding or from motorized platforms suspended from the building's roof. Progress is measured in panels per day per crew, and on a large building, the curtain wall installation may take a year or more, progressing from the lower floors upward as the structural frame above is completed. The visual logic of height. There is something that experienced structural engineers understand about tall buildings that the rest of us tend not to think about at all. A skyscraper does not simply stand up. It stands up differently depending on how tall it is, and the relationship between a building's height and the structural strategy required to achieve that height is one of the more elegant subjects in engineering. For buildings up to roughly 40 or 50 stories, a conventional moment frame, a rigid grid of columns and beams connected at their joints, can handle both gravity and lateral loads with reasonable efficiency. As buildings get taller, the proportion of the structure devoted to resisting lateral loads grows rapidly, and the simple rigid frame becomes increasingly uneconomical. Between roughly 50 and 100 stories, buildings typically use some combination of a stiff core, outrigger trusses connecting the core to the perimeter columns at certain mechanical floors, and perimeter belt trusses that distribute lateral loads around the building's perimeter. This system, the bundled tube, the brace tube, the frame tube, the outrigger system, represents the structural vocabulary of the majority of the world's tall buildings, developed primarily through the work of structural engineers like Fazlur Rahman Khan, who worked at the Chicago firm Skidmore, Owings and Merrill, in the 1960s and 1970s, and whose structural innovations made buildings like the Willis Tower, formerly known as the Sears Tower, and the John Hancock Center possible. Kahn understood that the structural problem of a very tall building was fundamentally an aerodynamic problem. The wind was the dominant design force, and the structure had to be organized to resist wind as efficiently as possible. His insight was that if the exterior of the building could be made to behave structurally like a hollow tube, with the perimeter columns and spandrel beams acting together as a single structural element, the building could resist lateral loads far more efficiently than a rigid interior frame could. The columns would be in compression on one side of the building when wind pressed against it, and in tension on the other side, the whole building working together like a giant vertical cantilever rooted at the ground. This tube concept, and the many variants that have been developed from it, is the structural idea that underlies most of the world's tallest buildings. The specific geometry of the tube, whether it is a single tube, a bundled cluster of tubes as in the Willis Tower, a diagrid of diagonal members as in the Hearst Tower in New York, or the Swiss Re Tower in London, or an outrigger-enhanced core and perimeter system, varies from building to building based on the specific conditions of height, wind, seismicity, and architectural intent. But the underlying logic is the same. Organize the structure so that the whole building, not just individual members, resists the lateral forces that are the governing design challenge of tall buildings. The buildings that breathe one of the most persistent misconceptions about skyscrapers among people who are not involved in their construction or engineering is that they are essentially rigid, fixed objects that stand immovably against whatever forces act on them. The reality is precisely the opposite. And understanding this helps make sense of some of the more remarkable engineering solutions that tall buildings require. A tall building in a significant wind event is not stationary. It moves. The upper floors of a super tall building in a strong wind may displace horizontally by 1, 2, or 3 feet from their position in still air. This movement is carefully calculated and controlled by the structural engineers. It is a design behavior, not a failure, but it is real, and it is perceptible to the building's occupants if it exceeds certain thresholds. The human body is surprisingly sensitive to lateral acceleration, to the feeling of being gently but persistently pushed sideways as the building moves. Structural engineers who design tall buildings have to work not just to keep the structural stresses within safe limits, but to keep the building's lateral accelerations within comfort limits that the occupants of the upper floors can tolerate without experiencing disorientation or nausea. The relevant standard is not strength, but perception, and the perception threshold for lateral acceleration is actually quite low, fractions of a percent of gravitational acceleration, felt as a barely perceptible gentle swaying in moderate winds. Managing this comfort criterion is one of the more challenging aspects of super tall building design, and it has driven the development of some genuinely remarkable engineering solutions. The most elegant of these, and one of the most fascinating objects in the hidden world of tall buildings, is the tuned mass damper. A tuned mass damper is, in basic concept, a large mass, typically steel or concrete, ranging from a few hundred to over 1,000 tons, depending on the building, suspended from the structural frame by cables or springs, and connected to the building structure through hydraulic damper devices. When the building sways in one direction under wind loading, the mass, by inertia, tends to remain stationary. It resists the movement. The hydraulic dampers connecting the mass to the building structure convert this relative motion into heat, dissipating energy. Properly tuned to the building's natural sway frequency, the mass damper acts as a kind of mechanical counterweight that absorbs the energy of oscillation, reducing the amplitude of the building's response to wind. The most famous tuned mass damper in the world is the one at Taipei 101, the tower in Taiwan that was the world's tallest building from its completion in 2004 until 2010. The Taipei 101 damper is a steel sphere weighing approximately 730 metric tons, suspended by cables from the 92nd floor down to the 88th floor in a spectacular open atrium visible to building visitors. It moves visibly during typhoons, swinging through arcs of several feet, silently absorbing energy while the building around it holds still. It is one of those engineering objects that has a certain straightforward drama to it, a giant pendulum, doing its job quietly in the heart of the building while the storm rages outside. Not all tuned mass dampers are as visible or as dramatic as the one at Taipei 101. Many are concealed in dedicated mechanical spaces, accessible only to maintenance engineers, doing their work invisibly. But they are there, in buildings all over the world, quietly counteracting the forces that would otherwise make a tall building's upper floors uncomfortable to occupy. The building site at midnight. By the time a skyscraper's structural frame has risen to its full height, the construction site has become something that would be almost unrecognizable to someone who had only seen it during the excavation phase. Where there was once a pit, there is now structure. Column lines rising from the basement through dozens of floors, core walls enclosing the elevator shafts and stairs, floor slabs spanning between the frame elements, the curtain wall progressing up the lower floors, tower cranes riding the rising structure. The activity on the site has diversified. Where the early phases were dominated by a relatively small number of very large operations, the excavation, the foundation, the structural erection. The building is now populated by dozens of distinct trades, each working in its own zone of the structure, each with its own schedule and its own sequence requirements, each dependent on other trades having completed their work before it can proceed. The mechanical rough-in crews are installing ductwork and pipe in the lower floors, threading their systems through the structural frame before the interior walls are built. The electrical crews are running conduit and pulling wire. The fire suppression crews are installing sprinkler pipe. The curtain wall crews are working on the lower facade. The elevator crews have begun their work in the shafts. The concrete pump is still running on the upper floors, pouring the core walls for the latest level. And somewhere in the city around this site, a fabricator is completing the next delivery of structural steel. A glass manufacturer is loading curtain wall panels onto a truck. A concrete plant is batching the mix for tomorrow's pour. The supply chain that feeds this single building site extends outward in all directions, to mills and factories and fabrication shops and quarries and chemical plants, in a network so extensive that fully mapping it would be a documentary in its own right. The building is rising, floor by floor, panel by panel, connection by connection. The city is sleeping, and the work continues, and the skyline is changing in increments so small that no single night reveals them, but so relentlessly continuous that by the time most people notice, the thing is already there, already part of the city, already taken for granted, as if it had always been standing against the sky, waiting for someone to build a city around it. There is a version of a skyscraper that most people carry in their heads without realizing it. It is the version visible from the outside. The glass and steel facade, the lobby with its polished floors and security desk, the elevator buttons, and the long view from an upper floor window on a clear day. This is the skyscraper as experienced by the people who work in it or visit it, and it is a perfectly reasonable version of the thing. It just happens to be missing most of what is actually there. A completed skyscraper contains, within its walls and between its floors and beneath its ceilings and behind its access panels, an infrastructure of extraordinary complexity. Miles of electrical cable, miles of water pipe, ventilation systems capable of moving enormous volumes of air through hundreds of thousands of square feet of occupied space every hour of every day. Elevator systems of a sophistication that most people, even frequent users, would find genuinely surprising. Fire suppression systems, communications infrastructure, building management systems that monitor and control thousands of individual components simultaneously. Emergency power systems, fuel storage, water storage, pumping stations distributed at intervals up the building's height. A tall building is not simply a structure. It is a vertical city. And like any city, it depends on systems, invisible, continuous, largely unnoticed systems that must work reliably every moment of every day, from the day the building opens until the day, decades later, when it is eventually replaced. Understanding these systems and how they are designed and installed reveals something genuinely unexpected about skyscrapers. The structural engineering, the part most people find most impressive, is, in a certain sense, the more straightforward part of the problem. The structural system is a single integrated design, built once in a defined sequence, and then essentially finished. The building systems, the mechanical, electrical, plumbing, and fire protection systems that animate the structure, are a different kind of problem entirely. They are living systems, designed for continuous operation, requiring ongoing maintenance, subject to obsolescence, and capable of failure in ways that a steel column or a concrete core wall simply cannot. This is where the real complexity of tall buildings lives. The building within the building. Every significant skyscraper contains floors that are not rentable, not usable by occupants, and not visible in the building's promotional materials. They appear in floor plans as blank zones, labeled simply as mechanical floors or service floors, and they are among the most important spaces in the entire building. Mechanical floors exist because the engineering systems in a tall building cannot be compressed into a single basement plant room and expected to function across 60, 80, or 100 stories of occupied space. The physics simply do not cooperate. Water pressure, for instance, is limited by what the pipes at the lowest point of any given pressurized zone can safely contain. And a water column 100 stories tall would generate pressures at the bottom that no conventional plumbing fixtures could withstand, and no standard pipe system could safely contain. Air handling has its own constraints. The duct sizes required to carry conditioned air the full height of a tall building from a single central plant would be so large as to consume substantial floor area on every floor they pass through. Electrical distribution at high voltage over very long distances requires transformation at intermediate points to maintain efficiency and safety. The solution to all of these problems is the same. Distribute the building's engineering systems vertically, with intermediate service floors at regular intervals up the building's height, typically every 15 to 25 floors, depending on the specific systems and the engineering requirements. These mechanical floors serve as the relay stations of the building's infrastructure, the places where systems from below are received, transformed, or redistributed, and sent upward again in a form suitable for the next zone of floors. A mechanical floor in a large office tower is a strange and somewhat alien environment. The floor-to-ceiling height is typically greater than on office floors, accommodating the large equipment that lives there. The space is filled with the sound of fans, compressors, pumps, and the white noise of moving air and water. Ducts and pipes run in all directions. Electrical switchgear lines the walls. Cooling towers or heat exchangers may occupy portions of the space. Everything is labeled, everything is color-coded, and everything is, to the uninitiated, almost completely incomprehensible. Mechanical engineers who specialize in tall buildings develop an intimate familiarity with these spaces that is almost proprietary. They know the equipment, the control logic, the failure modes, the maintenance requirements. They know that the cooling coil in Air Handling Unit 7 on the 32nd mechanical floor has a tendency to freeze up in cold weather if the outside air damper control is not properly calibrated. They know that the pressure-reducing valve on the domestic water system serving floors 40 through 58 requires recalibration every 18 months. This operational knowledge, accumulated over years of managing a specific building's systems, is as specialized and as valuable as the engineering that originally designed those systems, and it resides almost entirely in the heads of the building engineers and facilities managers who spend their working lives in spaces that most of the building's occupants never visit and rarely think about. Elevators. The technology that made everything possible. Here is a fact about skyscrapers that tends to reorganize how people think about them once they have encountered it. The structural and architectural engineering that allows buildings to stand at great heights has existed in various forms for a very long time. Ancient Romans built multi-story apartment buildings, insulae, that sometimes reached 6 or more stories in height. Medieval builders constructed cathedrals and towers of remarkable ambition. The technical knowledge required to stack floors vertically has never been the hard part of the problem. What limited the practical height of occupied buildings for essentially all of human history was not structural engineering. It was the requirement that people had to walk up. Above 5 or 6 floors, the physical effort of climbing stairs made upper floors significantly less desirable than lower ones, and therefore worth less rent. Above 10 or 12 floors, in a world without mechanical assistance, occupied use became essentially impractical. The upper floors of a 15-story building in a world without elevators would have been suitable only for storage or for very highly motivated occupants with exceptional physical fitness. The elevator, specifically the safety elevator, equipped with a device that prevents the car from falling if the hoisting cable breaks, changed this equation completely. Elisha Graves Otis demonstrated his safety elevator at the New York Crystal Palace Exposition in 1854 in a manner that was, for a technical demonstration, almost theatrical. He had himself raised to a considerable height in an open elevator car, then ordered the hoisting rope to be cut with an axe. The safety device engaged. The car remained stationary. The crowd, which had expected the worst, was instead treated to a demonstration that a new kind of building was now possible. The first passenger safety elevator in a commercial building was installed in the Hochwout building in New York in 1857. And within 30 years, the combination of Otis's safety elevator and the steel frame structural system had produced the first true skyscrapers in Chicago. The relationship between these two technologies is not incidental. It is constitutive. The skyscraper, as a building type, is an elevator building. Without the elevator, the structural accomplishment of building tall is an architectural curiosity. With it, it becomes one of the defining forms of modern urban civilization. Modern elevator technology has traveled a very long way from Otis's rope and counterweight demonstration in 1854, though the fundamental principles would still be recognizable. A typical high-rise elevator today consists of a car suspended in a shaft by steel wire ropes, counterbalanced by a counterweight on the opposite side of the sheave at the top of the shaft, driven by an electric motor through a gearless traction machine. The car and counterweight together, in a properly balanced system, require the motor to provide only the energy needed to move the net load difference between them, making the system considerably more energy efficient than it would be without the counterweight. What has changed profoundly is the control intelligence that manages elevator systems in tall buildings. And this is where modern elevator engineering becomes genuinely impressive. A tall office building with multiple elevator shafts serving multiple zones of floors faces a traffic management problem of considerable complexity. On a Monday morning, when thousands of workers arrive at the lobby over a period of an hour or two, the demand on the elevator system is extreme and highly directional. Almost everyone wants to go up, and they want to go up now. At lunchtime, demand reverses and disperses, people moving in all directions between floors in the lobby. At the end of the working day, the down direction dominates again. Throughout the day, there are random individual calls from individual floors that must be served efficiently without creating unacceptably long wait times. Managing this with maximum efficiency requires sophisticated dispatch algorithms that have become increasingly complex over the decades. Early systems simply responded to hall calls in sequence, serving each floor in turn as a car passed it, going up or down. Modern destination dispatch systems, now common in new high-rise buildings, require passengers to enter their destination floor before they board the elevator, at a keypad or touchscreen in the elevator lobby rather than inside the car. The system then groups passengers by destination, assigning each passenger to a specific car that will serve their floor, and coordinates all the cars in the group to minimize total travel time for all passengers simultaneously. The efficiency gains from destination dispatch are substantial. Elevator systems using this approach can move significantly more passengers per hour than conventional call button systems, using the same number of cars and shafts, which in a tall building represents a significant reduction in the amount of floor area that has to be devoted to elevator shafts. Space that can instead be rented or used productively. In super tall buildings, those exceeding roughly 1,000 feet, the elevator problem becomes even more interesting. At this scale, the number of shafts required to serve the building, if all elevators ran the full height from lobby to top floor, would consume so much floor area that the building's commercial efficiency would be unacceptable. The solution, developed by Otis and other elevator manufacturers for buildings like the World Trade Center in New York and the Sears Tower in Chicago, is the Sky Lobby system. Passengers board express elevators in the ground floor lobby that carry them non-stop to Sky lobbies at intermediate floors, typically at roughly 1/3 and 2/3 of the building's height. At the Sky lobby, they transfer to local elevators that serve the floors above and below. Because the express elevators and local elevators share shaft space in the same vertical zone, and because the Sky lobbies consolidate passenger transfer into a small number of floors, the overall shaft area consumed is significantly less than a system of full-height elevators would require. There is also, in the elevator engineering world, a technology that has been commercially deployed on a limited basis and represents the most significant departure from the Otis paradigm since the original safety elevator. Linear motor elevators, systems that drive the elevator car using linear induction motors built into the shaft walls rather than rope and sheave, have been installed in a small number of buildings and offer the intriguing theoretical possibility of elevator cars that do not need ropes, that can travel both vertically and horizontally within a shaft network, and that could potentially serve a building with a geometry that no rope-based system could accommodate. The technology is still developing, but it suggests that the elevator, as an engineering system, has not finished its evolution. How a skyscraper gets its water as an engineering problem is one of those things that most people do not think about until it stops working, at which point it becomes all they can think about. In a tall building, the delivery of water to the upper floors, reliable, pressurized, clean, cold water for drinking and washing, and separately treated water for fire suppression, involves engineering that is significantly more complex than anything in the water system of an ordinary building. The fundamental problem is pressure. The municipal water supply arrives at the base of a building at a pressure that is suitable for low-rise buildings, but entirely insufficient to push water to the upper floors of a super-tall. Water pressure falls with height, approximately 0.43 pounds per square inch for every foot of elevation, meaning that to deliver water at a usable pressure to a floor 100 feet above the street, the supply pressure at the ground would need to exceed 43 pounds per square inch just to overcome the height, before accounting for any pressure losses in the piping. At 200 feet, 86 pounds per square inch. At 500 feet, the numbers become extreme. The solution is to not attempt to supply the entire building from the bottom. Instead, tall buildings use a series of pressure zones, with booster pumps at the base of each zone pressurizing the water supply for that zone to appropriate levels, and intermediate holding tanks at mechanical floors acting as reservoirs that can be refilled during low demand periods and drawn down during peak demand. These tanks, sometimes open storage tanks, sometimes sealed pneumatic pressure tanks depending on the system design, provide both storage capacity and a buffer between the pumping system and the distribution network. The gravity tank, historically the most common approach to rooftop water storage in tall buildings, works on a beautifully simple principle. Water is pumped to a tank on the roof or upper mechanical floor, and the weight of the water in the tank, its head pressure, provides the driving force for distribution to the floors below. No pump is needed for normal distribution. Gravity does the work. The pump runs periodically to refill the tank as it is drawn down by use. The familiar water towers of New York City, those distinctive wooden cylinders on top of mid-century office buildings and apartment blocks, are the most visible expression of this principle. A low-technology solution to the pressure problem that is elegant in its simplicity, reliable in operation, and requiring only occasional pump maintenance to sustain essentially indefinitely. In modern high-rise buildings, the gravity tank approach is often combined with booster pumping systems in a hybrid that provides the reliability of gravity-fed distribution with the flexibility of on-demand boosting for zones or fixtures that require higher pressure than the gravity head alone can provide. Water quality in tall buildings adds another layer of complexity. In any water system with long pipe runs and storage tanks, there is a risk of the water sitting long enough in certain dead-end sections of pipe or in frequently used tanks to create conditions favorable to the growth of Legionella bacteria, the organism responsible for Legionnaire's disease. Modern buildings are required to implement water management programs that address this risk through a combination of system design, temperature management, periodic flushing of infrequently used outlets, and chemical treatment where appropriate. Building engineering staff maintain detailed records of water system maintenance, and in many jurisdictions, this is now a regulatory requirement subject to inspection. Electricity at altitude a tall building's electrical system is, in terms of its complexity and the engineering judgment required to design it, comparable to the electrical distribution system of a small town. The parallels are not merely rhetorical. A large office tower may house 10,000 or more occupants during the working day, consuming electrical power for lighting, mechanical systems, elevators, data infrastructure, food service, and all the other functions of a dense human environment. Power arrives at the building from the utility company at medium or high voltage, typically several thousand volts, through utility cables that enter the building in underground vaults or basement electrical rooms. This high voltage supply is immediately stepped down through transformers to voltages suitable for distribution within the building. The transformers, together with the main switching and protective equipment, occupy substantial space in the building's electrical rooms. And on a large building, there may be multiple primary electrical rooms at different levels. Fed from the utility connection and feeding the distribution systems for their respective zones. From the main electrical rooms, power is distributed upward through the building via bus ducts, enclosed metal duct systems carrying large copper or aluminum bus bars that can carry enormous currents efficiently over the height of the building, or through banks of large cables in dedicated electrical shafts. At each floor or group of floors, power is tapped from the riser system and routed to the individual tenant electrical panels that serve each floor. The separation of circuits within a tall building is carefully engineered for both efficiency and resilience. Life safety systems, emergency lighting, exit signs, fire alarm systems, pressurization fans for stairwells, and a defined number of elevators are connected to emergency power systems that come online automatically in the event of a utility power failure. These emergency power systems typically consist of diesel generators, large, building-specific generators housed in mechanical floors or the basement, fueled by diesel stored in tanks within the building, and tested regularly under load to ensure that they will start reliably when needed. The electrical load of a major skyscraper varies enormously across the day and the week, and managing this variation is part of the building engineer's ongoing responsibility. Demand charges, the portion of the electricity bill based on peak demand rather than total consumption, create financial incentives to minimize the peak load drawn from the utility at any given moment, which in a large building can be managed through load scheduling strategies. Demand-controlled ventilation that reduces the mechanical system's electricity consumption during periods of low occupancy, and increasingly through battery storage systems that store energy during low-cost periods and release it during peak demand periods. The intelligence of modern building electrical systems has grown dramatically in the past 2 decades. Building management systems, integrated computer platforms that monitor and control the building's electrical, mechanical, lighting, and sometimes elevator systems from a single interface, can now implement optimization algorithms that adjust dozens of systems simultaneously in response to occupancy patterns, utility pricing signals, weather conditions, and equipment status. A building management system in a well-operated major skyscraper is running thousands of control loops simultaneously, making small adjustments to temperatures, pressures, fan speeds, and lighting levels across the entire building. continuously and automatically, with the building's engineers monitoring the overall picture and intervening only when conditions fall outside the normal operating envelope. It is a degree of operational sophistication that is invisible to the building's occupants, who experience only its results. A room that is neither too hot nor too cold, lights that are on when needed and off when not, elevators that arrive promptly and travel smoothly. The system works when it is not noticed, the wind problem. Earlier in this story, the structural response to wind loading was discussed in terms of the tuned mass damper, the large, suspended counterweight that absorbs energy when a building sways in a storm. But the structural accommodation of wind is only one dimension of the wind problem in a tall building. There is another dimension that is more subtle, and in some respects more interesting, because it reveals the way in which a building that appears to be a passive object is actually in continuous dynamic interaction with the air moving around it. Wind does not flow around a tall building in a simple, predictable way. At the upper floors, where the building extends above the surrounding urban fabric, wind speeds are typically much higher than at street level, as much as 2 or 3 times higher at the very top of a super tall building than at grade. As wind hits the building's face, it separates at the edges, creating a complex wake pattern on the downwind side. In certain conditions, this separation creates organized vortices, rotating columns of air that shed alternately from each side of the building at a frequency that depends on the wind speed and the building's cross-sectional dimensions. If this vortex shedding frequency approaches the building's natural sway frequency, the frequency at which the building tends to oscillate, the result is resonance. The building, instead of damping the aerodynamic forces, amplifies them, responding with increasing amplitude as energy is added to the system with each shed vortex. This phenomenon, called vortex-induced vibration, is the aerodynamic equivalent of pushing a child on a swing in rhythm with its natural period, and it can produce building motions far greater than those caused by the direct pressure of the wind itself. Managing vortex-induced vibration is one of the key challenges in super tall building design, and it is addressed primarily through the building's shape rather than through structural modifications. Buildings with rounded corners shed vortices less readily than buildings with sharp corners. Buildings with tapered profiles, where the cross-section changes size as the building rises, disrupt the formation of organized vortices by changing the shedding frequency at different heights. Buildings with aerodynamic modifications to their form, setbacks, through holes, twisted profiles, are all, in part, engineering responses to the wind problem expressed in architectural terms. The Burj Khalifa in Dubai, currently the world's tallest building at over 2,700 feet, has a distinctive spiraling, Y-shaped floor plan that was developed specifically to confuse the formation of organized wind vortices. As the building rises, the 3 wings of the Y-plan rotate and reduce in size, constantly changing the aerodynamic character of the structure and preventing the coherent vortex organization that would otherwise cause problematic resonant response. The shape of the Burj Khalifa is simultaneously an architectural expression and a wind engineering solution, the 2 goals so thoroughly integrated that it is impossible to separate them. Wind tunnel testing is an essential part of the design process for any tall building of significance. Scale models of the building, surrounded by models of the neighboring urban context that affect the local wind environment, are placed in boundary layer wind tunnels where the airflow simulates the turbulent wind profile of a real urban atmosphere. Instruments measure pressure distributions over the building's surface, overall force and moment responses, and accelerations at representative floor locations. The results are used to validate or refine the structural and aerodynamic design, and to assess the comfort of pedestrians at ground level. Where the wind deflected downward by a tall building can create local acceleration zones that are genuinely unpleasant, or in severe cases, dangerous, to walk through. Some of the most technically sophisticated wind tunnel work in the world is performed in facilities specifically oriented toward tall building testing, including the RWDI Wind Engineering Facility in Guelph, Canada, and the Kermak-Peterka Peterson Facility in Colorado, where engineers have subjected models of the world's tallest and most architecturally complex buildings to the simulated wind environments of every major climate zone on Earth. Fire, the problem that shaped everything. The history of fire in tall buildings is one that the engineering community has spent more than a century trying to write in a way that does not end badly. It has not always succeeded. The story of fire in skyscrapers is honestly a story of catastrophic failures that gradually produce the engineering knowledge, the regulatory frameworks, and the design practices that make modern tall buildings as safe as they are today. The fundamental problem of fire in tall buildings is that height creates conditions that are, from a fire engineering perspective, genuinely hostile. Tall buildings create their own internal weather. Air pressure differences between the inside and outside of the building, driven by temperature differentials and by the stack effect, the natural tendency of warm air to rise in a tall enclosed sabong. This stack effect, which is most pronounced in cold weather, creates pressure differentials that can drive smoke movement through a tall building with remarkable speed and intensity, carrying combustion products far from the seat of the fire to floors and zones that are otherwise completely uninvolved. The engineering response to this problem has evolved dramatically over the past century, driven by a series of events whose lessons were bought at enormous cost. The Triangle Shirtwaist Factory fire of 1911 in New York, though not a skyscraper fire, drove the development of fire-resistive construction requirements and occupant egress standards that shaped building codes for decades. The 1945 crash of a B-25 bomber into the Empire State Building, which caused fires on several floors but was contained by the building's fire-resistive construction, demonstrated both the resilience of properly designed tall buildings and the importance of compartmentalization. The One Meridian Plaza fire in Philadelphia in 1991, which burned uncontrolled for 18 hours on 8 floors of a 38-story building because the building lacked automatic sprinklers, was the event that finally drove comprehensive sprinkler requirements for high-rise buildings throughout the United States. A modern high-rise building's fire protection systems are layered and redundant in a way that reflects this hard-won understanding. Automatic fire sprinklers, individual sprinkler heads positioned at regular intervals across every floor, connected to pressurized water supply pipes, respond to heat independently of any human action or central control. Each sprinkler head activates individually when the temperature at that specific location rises above its calibrated threshold, discharging water directly onto the fire below. Contrary to the impression given by movies, sprinklers do not all activate simultaneously throughout the building when any single sprinkler activates. The individual thermal response of each head means that only those heads directly above the fire are typically activated, limiting water damage to the fire zone. Smoke control is addressed through a combination of pressurized stairwells, where mechanical fans maintain positive air pressure in the stair enclosures, preventing smoke from entering the primary evacuation route, and smoke exhaust systems in occupied areas that dilute and remove smoke-laden air. Elevators are recalled to the ground floor and removed from normal service when a fire is detected, making them unavailable to occupants attempting to evacuate, but available to firefighters who can override the control and use them with special keys. The means of egress from a tall building, the stairs, are engineered to specific standards of width, configuration, location, and fire resistance that are among the most carefully regulated aspects of high-rise building design. The lessons of the September 11, 2001 attacks on the World Trade Center towers, and specifically the analyses of the evacuation that occurred before the towers collapsed, led to significant revisions in the egress requirements for very tall buildings in the subsequent edition of the Model Building Codes. Stair widths were increased. Additional stairs were required. Photoluminescent path markings, visible even through heavy smoke, were mandated for stairwells in very tall buildings. Areas of refuge, structurally protected spaces within the stair enclosures where mobility-impaired occupants can wait for assisted evacuation, were codified. The building codes that govern fire safety in tall buildings today are not arbitrary regulations. They are, each requirement, the accumulated response to events that revealed specific vulnerabilities, calibrated over decades by committees of engineers, fire safety professionals, building officials, and researchers who have spent careers studying how fires start, spread, and are eventually controlled in the most complex building environments on Earth. The inspection system nobody talks about, construction inspections, are among the least glamorous aspects of building a skyscraper, and they are also among the most important. They are the mechanism by which the gap between what was designed and what was actually built is measured, and, when necessary, corrected before it becomes a problem that cannot be corrected. On a major building project, the inspection system is layered and involves multiple parties with different roles and different authorities. The design team, the architect, and the structural, mechanical, electrical, and other engineers of record maintains responsibility for ensuring that the building is constructed in accordance with their design intent. Their field staff visit the site regularly to observe construction, review contractor submittals, respond to requests for information, and approve or reject deviations from the design that the contractor proposes for practical reasons. Independent special inspection agencies, third-party testing and inspection firms hired by the building owner, but reporting to the design team and the building department, provide continuous or periodic inspection of critical work that cannot be verified after the fact. Concrete work is special inspected throughout. Cylinders of concrete are sampled from each truck delivery, cured under controlled conditions, and tested for compressive strength at defined ages to verify that the material meets specification. Structural steel connections are inspected for bolt installation and welding quality. Fireproofing applied to structural steel members is tested for thickness and adhesion. Foundation materials are tested in the laboratory and inspected in the field. The local building department, the government authority that issued the building permit, maintains its own inspection program, with code enforcement officers who visit the site at defined stages of construction to verify compliance with the building code. These inspections are not optional, and the building cannot proceed past certain stages of construction without a sign-off from the building department inspector. In New York City, the inspection and approval process for a major skyscraper involves so many different city agencies, each with their own inspection programs and approval requirements, that coordinating these inspections is itself a full-time task for the construction management team. The Department of Buildings, the Fire Department, the Department of Environmental Protection, the Department of Transportation for any work affecting public streets. Each has its own inspector, its own schedule, its own forms, and its own definitions of what constitutes an acceptable installation. The system is imperfect. Inspectors have varying levels of expertise and varying degrees of rigor. Special inspection agencies, hired by owners, have a financial relationship with the people whose work they are inspecting that creates at least a theoretical tension between commercial and professional obligations. Building departments in many cities are understaffed relative to the volume of construction they are responsible for overseeing. But the basic logic of the inspection system, multiple independent parties verifying critical work at critical stages, has proven itself over many decades as the most reliable available mechanism for catching and correcting construction defects before they become permanent. The buildings that have failed structurally or mechanically in service, when investigated afterward, have frequently revealed not that the inspection system failed to require the right work, but that the inspection system was somehow bypassed, compromised, or inadequate for the specific risk that ultimately materialized. The best tribute to the inspection system is not the buildings that have failed. It is the far larger number that have not. The workers the skyline forgets. A completed skyscraper carries no record of the people who built it. The architectural drawings bear the name of the architect. The lobby plaque, if there is one, acknowledges the developer, the design firm, perhaps the general contractor. The building's Wikipedia page lists the structural engineer, and sometimes the height in feet and the number of floors. Nowhere in any of this is there an accounting of the individual human beings who actually constructed the thing. On a major skyscraper project, the peak construction workforce might number several thousand workers on a single day. Over the full course of construction, from the first geotechnical drilling to the final certificate of occupancy, the total number of individual workers who have contributed labor to the project, who have driven a truck, operated a crane, poured concrete, installed reinforcing steel, bolted structural connections, installed ductwork, pulled electrical wire, fitted plumbing pipe, applied fireproofing, installed curtain wall panels, hung drywall, laid floor tile, installed ceiling systems, tested equipment, calibrated controls, might be 10,000, 15,000, 20,000 people. They come from the full spectrum of the construction labor force. Journeymen and apprentices in the unionized trades, ironworkers, operating engineers, teamsters, carpenters, plumbers, electricians, laborers, each with their own training history, their own union local, their own set of jurisdictional work rules that define precisely which tasks fall within their trade. Non-union subcontractors, depending on the project and the local labor market. Specialty subcontractors, curtain wall installers, elevator mechanics, fire suppression specialists, who may have traveled from considerable distances because the specific skill their work requires is not widely available in the local market. Among the less discussed aspects of skyscraper construction is the degree to which the workforce changes across the life of the project. The workers who drive the excavation equipment are not the same people who erect the steel frame. The ironworkers move on to the next project when the structural phase is complete. The curtain wall crew arrives after the frame is up and leaves when the facade is done. Each trade has its peak and its departure, and the composition of the workforce on the site at any given moment reflects where the project is in its sequence. Workers on a construction project develop a sense of time that is measured not in calendar dates, but in phases. You know you are approaching the end of your phase when the pace picks up, when the punch list for your scope of work begins to dominate the daily conversation, when you can see the next trade beginning to arrive in areas where your work is complete. There is a particular satisfaction in the construction trades that is difficult to replicate elsewhere. The satisfaction of building something physically real, something that was not there before and is now there, something that will stand long after the people who built it are gone. Ironworkers who have retired speak of specific buildings they erected with a pride that is specific and personal. That building, that floor, those connections. Concrete finishers remember particular pours. Electricians remember the long days of pulling wire on a complicated floor where the conduit routing was a puzzle that took a week to solve. None of this appears in the building's history. The skyscraper, once complete, becomes an object, a fixed point in the city, a thing that is simply there. The human effort that created it is invisible in the finished product, in a way that effort in most other fields is not. A painting carries the evidence of the painter's hand. A piece of furniture carries the marks of the craftsperson. A building, properly finished, conceals everything: the construction joints, the formwork marks, the bolt heads, the penetrations, the thousands of small imperfections that were found, corrected, and covered up in the process of completing the work. This invisibility is, in a practical sense, the measure of a job well done. In a human sense, it is worth pausing over. The city's skyline, seen from a distance at night, is one of the more beautiful things that contemporary civilization produces. The lights in those towers, the reflections in the glass, the way the top floors catch the last light of sunset while the streets below are already in shadow. All of it is, at some level, the accumulated result of an extraordinary quantity of human skill, human labor, human problem-solving, human patience, and human discomfort. People worked in the cold to build those towers. People worked at height, in wind, in summer heat, in the compressed and awkward spaces of mechanical floors. People drove trucks at 3 a.m. to deliver concrete that had to keep flowing. People stood on iron beams several hundred feet in the air and drove bolts home with air-powered tools, while the city went about its business far below. They are not remembered by name. They are remembered in the only way construction work allows, in the buildings themselves, in the thing that is there now that was not there before, standing against the sky, holding thousands of people in the air above the city. Tonight, somewhere in the world, more of these workers are at it. The night shift is running. The concrete is moving. The crane is turning. The scaffolding sways slightly in the wind on the upper floors. And a glazier, in a high-visibility vest, checks the seal on a curtain wall panel before signing off and heading back inside for coffee. and far below, the city sleeps without knowing any of this is happening. There is a particular moment in the life of a skyscraper construction project that the people who work on these buildings describe with a consistency that suggests it is genuinely universal. It happens sometime after the structural frame has reached its full height. After the tower crane has completed its last climbing cycle and sits at the top of the structure like a flag planted on a summit. The building is, at this point, structurally complete. The floors are all there. The core walls are poured. The curtain wall is progressing up the facade in its methodical floor-by-floor sequence. And yet the building is nowhere near finished. This is the moment when the full complexity of what remains becomes apparent in a way it somehow was not before. The shell exists, but the shell is only the container. Everything that will make this container into a place where people actually live or work. The walls, the ceilings, the floors, the lighting, the plumbing fixtures, the data infrastructure, the fire alarm devices, the elevator finishes, the lobby stone, the rooftop mechanicals, the signage, the landscaping, the loading dock equipment, the security systems. All of it still has to happen, floor by floor, room by room, connection by connection. This phase of construction is called the interior fit-out, or sometimes the interior build-out, and it is, in terms of sheer volume of work and number of people involved, frequently larger than everything that came before it. It is also the phase that most people, even those who have followed a construction project with interest from the outside, tend not to understand very well. The structural phase is visible and legible. You can watch the building grow floor by floor and understand, in a general way, what is happening. The fit-out phase happens behind an opaque curtain wall, in hundreds of rooms simultaneously, in a complexity and density of parallel activity that is almost impossible to comprehend from the outside. This is where a skyscraper stops being a structure and becomes a building. The interior build-out, when the shell becomes inhabited. The interior fit-out of a major commercial skyscraper involves a sequence of work that is, in its broad outlines, the same on every project, but differs in its details in ways that keep the people managing it continuously occupied. The sequence matters because most interior work is dependent on prior work having been completed. You cannot install a ceiling before the ductwork above it is in place. Cannot install the ductwork before the structural penetrations for it have been made. Cannot install flooring before the subfloor is prepared. Cannot install the subfloor before the concrete slab has cured and been surveyed for flatness. The sequencing of interior work on a floor-by-floor basis across a building of 60 or 80 floors with a dozen or more active trades working simultaneously is a scheduling problem of genuine complexity. The construction manager responsible for this phase typically maintains detailed 3-week look-ahead schedules that track the status of work on every floor, identify the critical dependencies that constrain progress, and flag the emerging conflicts between trades that will need to be resolved before they become delays. Partition walls, the non-structural interior walls that divide open floor plates into individual offices, conference rooms, corridors, and service areas, are typically built from light-gauge steel stud framing covered with gypsum wallboard, a system that is fast to install, relatively inexpensive, acoustically reasonable when properly detailed, and easily modified if tenant requirements change in the future. The framing goes up first, then the mechanical and electrical rough-in work is installed within and above the framed space. Then the wallboard is installed and finished. Then the ceiling system is suspended below the structural slab above. Then the flooring is installed. Then the fixtures and devices and finish hardware that complete the space. Each of these steps involves different trades, different materials, different supply chains, and different inspection requirements. The coordination of the sequence across multiple floors, maintaining momentum while managing the inevitable disruptions, delayed material deliveries, trade conflicts over work sequence, discovered conditions that differ from what the drawings assumed, is the central management challenge of the fit-out phase. On a large project, the fit-out phase may involve 2,000 or more workers on a peak day, from dozens of subcontractors and sub-subcontractors, each with their own supervision structure, their own labor force, and their own interpretation of where their scope of work begins and ends, and how it interfaces with adjacent scopes. The construction manager's role during this phase is less like engineering and more like diplomacy. The management of competing interests, limited space, shared resources, and mutual dependencies among parties who all have their own priorities and their own pressure to complete their work on schedule. The lobby deserves particular mention because it is the space in a commercial skyscraper that receives the most design attention and, proportionally, the most construction cost and effort relative to its floor area. The lobby is the building's face to the world, the first interior space that every visitor, tenant, and delivery person encounters, the space that establishes the building's character and quality in a way that no upper floor can replicate. As a result, lobby finishes in major commercial buildings tend toward materials, stone, metal, specialty glass, bespoke lighting systems, custom millwork that require skilled installation by craftspeople whose work is evaluated at a level of tolerance that is significantly more demanding than standard commercial construction. The installation of large format stone panels in a major building lobby, marble, granite, limestone, or travertine, in sheets that may measure several feet in each dimension and weigh hundreds of pounds, is a precision craft that combines the stonemason's traditional skill with the surveying precision of modern construction. The panels must be cut to exact dimensions, with joints that are both geometrically perfect and structurally sound, and the overall surface must be plumb, flat, and continuous across what may be a very large area. The stone itself, quarried in Italy, Spain, Brazil, India, China, or any of the other major stone-producing regions of the world, arrives at the site in crates, each piece individually numbered to correspond to a shop drawing that shows exactly where each panel goes and in what orientation, so that the natural veining patterns of the stone can be arranged in the deliberate, continuous flow that distinguishes fine stonework from merely adequate stonework. When the lobby is finally complete, when the stone is installed, the lighting is calibrated, the reception desk is in place, the elevator doors have received their finish panels, and the building signage has been applied, it tends to look as if it was always there, as if it required no particular effort, as if it simply is. This, in the construction trades, is the highest compliment. The commissioning process. Before a tall building can be occupied, Something has to happen that is neither construction nor design, but partakes of both. Every system in the building, every piece of mechanical equipment, every electrical circuit, every control loop, every elevator, every fire protection device, every communication system has to be tested, verified, adjusted, and demonstrated to be functioning in accordance with its design intent. This process is called commissioning, and it is one of the most time-consuming and underappreciated phases of any large building project. Commissioning begins long before the building is complete. The commissioning agent, a specialist firm hired to oversee this process, reviews the design documents during the design phase to identify potential conflicts or ambiguities that will create problems during commissioning. They develop commissioning plans that specify, for every system and every piece of equipment, the sequence of tests and verifications that will be performed. They attend factory testing of critical equipment before it is shipped to the site. They review contractor submittals to ensure that installed equipment will meet the specified performance requirements. And then, when the building systems are sufficiently complete to support testing, the commissioning process begins in earnest. Air handling units are started for the first time, and their airflow rates, temperatures, and pressure characteristics are measured and compared to design values. Balancing contractors adjust the dampers and diffusers on every branch of every duct system to achieve the specified airflow at every location in the building. Chilled water and heating water systems are balanced for flow. Pumps are tested at their design operating points. Control sequences are tested. Does the outside air damper modulate correctly in response to the CO2 sensor? Does the chiller sequence correctly when the first chiller reaches its capacity limit? Does the emergency generator start within the required time when the utility power is interrupted? Elevator commissioning involves a particularly thorough series of tests because the consequences of an elevator failure in service range from inconvenient to life-threatening, depending on the nature of the failure. Each elevator car is subjected to a series of safety tests that include overspeed governor testing, buffer testing, safety device testing, and load testing. The control systems are verified for correct behavior across a comprehensive range of operating scenarios. In many jurisdictions, elevator commissioning must be witnessed and signed off by a licensed elevator inspector from the relevant government authority before the elevator can be placed in service. Fire protection system commissioning is similarly thorough and similarly regulated. The fire alarm system must be tested device by device. Every smoke detector, every heat detector, every manual pull station, every sprinkler flow switch, to verify that each device activates correctly and that the correct response is triggered at the fire alarm control panel and at the connected systems. The smoke control systems must be tested under realistic conditions to verify that they achieve the required pressurization and exhaust flows. The fire department connection points, the inlets through which fire department pumper trucks can boost the building's sprinkler water supply, must be tested and documented. Commissioning a large building takes months. On a very large or complex project, it may take the better part of a year. The commissioning agent's final report, a document that records the results of every test, identifies any deficiencies that were found and corrected, and certifies that the building systems are operating in accordance with their design intent, is a thick document that represents an enormous investment of time and expertise. It is also, once the building is occupied, the essential reference document that the building's engineering staff will consult when systems behave unexpectedly, providing the baseline against which current performance can be compared. The Certificate of Occupancy. The Certificate of Occupancy is a document issued by the local building authority that formally certifies that a building, or a portion of a building, has been inspected and found to comply with the applicable building codes and is safe for occupancy. In the context of a skyscraper project, it is the document that authorizes the building's tenants to move in and the building systems to be operated under normal occupied conditions. Obtaining a certificate of occupancy for a major tall building is, in many jurisdictions, the culmination of an inspection process so extensive that managing it requires dedicated staff. In New York City, the final inspection process for a major building project involves sign-offs from the Department of Buildings on all structural work, all fire protection systems, all means of egress, all mechanical and electrical systems, all plumbing systems, all elevators, and all life safety systems. Each category requiring its own inspector, its own documentation package, and its own formal approval. Additional sign-offs may be required from the fire department, the Department of Environmental Protection for the building's wastewater connections, and the Department of Transportation for any work affecting public sidewalks or streets. The process of assembling the documentation required for the final certificate of occupancy, the test reports, the inspection records, the engineer's certifications, the manufacturer's product approvals, the ACE-built drawings, is a project management task that begins on a well-run project well before the construction is complete, because the volume of documentation required is too large to be assembled efficiently in the final weeks before occupancy is needed. On many large projects, the building opens in phases. A temporary certificate of occupancy is issued for the lower floors, allowing those floors to be occupied while work on the upper floors continues. This phased occupancy approach requires careful planning of the life safety systems because the building's fire protection, egress, and emergency power systems must be functional and compliant for any occupied portion of the building, even if the floors above are still under active construction with workers present. The day the certificate of occupancy is issued, or the first temporary certificate allowing the first tenants to move in, is a milestone that the project team experiences with a mixture of relief and something that is not quite joy, but is adjacent to it. The building exists. People will live or work in it, starting today or tomorrow. The years of planning, design, approval, excavation, structure, systems, and fit-out have produced something real and functional and permanent. The cranes will come down. The construction fences will be removed. The temporary floodlights and the generators and the site offices and the porta potties and the material hoists and all the other apparatus of the construction site will be disassembled and removed. And then the building will simply be there, as if it had always been there. The skyscraper after construction. The story of a skyscraper does not end at the certificate of occupancy. It barely begins there. A tall building is designed for a service life of 50, 75, or 100 years, a period over which it will be continuously maintained, periodically renovated, repeatedly adapted to changing tenant requirements, and changing technological standards. And eventually, if it survives long enough, reconsidered for either major rehabilitation or replacement. The maintenance of a tall building is a continuous operation that involves a permanent staff of engineers, technicians, and maintenance workers whose work is as invisible to the building's occupants as the original construction was to the city around it. These are the people who change the filters in the air handling units, lubricate the elevator guide rails, test the fire alarm system devices on a rotating schedule, monitor the chiller plants for signs of refrigerant leakage, inspect the curtain wall for sealant failures and glass breakage, maintain the building management system databases, and respond to the continuous stream of small problems that any complex system generates in the course of normal operation. The facade of a tall building requires particular ongoing attention. Glass curtain walls in urban environments are subject to thermal cycling, ultraviolet degradation of sealants, pollution deposition on the glass surface, and the occasional impact damage from wind-blown debris. The building's exterior maintenance equipment, the window washing rigs, the davit systems, the suspended scaffolding that hangs from anchors on the roof and travels down the face of the building, allows maintenance and inspection crews to access every square foot of the building's exterior at intervals determined by the building's maintenance program. In some cities, the window washing schedule for major tall buildings is itself a logistical exercise of some complexity. A very large building may have tens of thousands of square feet of glass on its exterior surface, and washing all of it on a reasonable schedule requires equipment, staff, and careful coordination with building management to avoid conflicts with interior window cleaning, exterior facade inspection, or sealant replacement work that may be occurring simultaneously on different sections of the building. Over the building's lifetime, major systems will be replaced. Chillers and cooling towers have service lives of 20 to 30 years. Elevators require major modernization, new control systems, new drive machines, new cab finishes every 20 to 30 years. Curtain wall sealants require repointing on a schedule of 15 to 25 years, depending on the materials and the exposure. Electrical switchgear and distribution equipment has useful lives of 30 to 40 years. All of this replacement work has to be designed, planned, and executed while the building remains fully occupied. The engineering challenge of replacing a major building system without disrupting the building's normal operation is, in its own way, as demanding as the original installation. There are skyscrapers in New York, Chicago, and other major cities that have been standing for 60, 70, 80 years, that have been renovated and modernized multiple times, that have had their systems replaced and their facades reclad and their lobbies redesigned, and that are still fully occupied, still functioning, still contributing to the life of their cities. The Empire State Building, completed in 1931, has undergone multiple major renovation programs and is currently operated with a level of energy efficiency that its original designers would have found genuinely remarkable. The Willis Tower in Chicago, completed in 1973, has had its mechanical systems comprehensively upgraded and its facade partially reglazed. These buildings are not museum pieces. They are functioning, adaptive organisms, structures that have found ways to remain relevant and viable across a span of time that includes multiple generations of technology, multiple cycles of economic boom and recession, and changes in the nature of office work that their designers could not have imagined. The timber question Among the more unexpected developments in tall building construction in the past decade is the emergence of a material that most people would consider the opposite of a skyscraper material: timber. Specifically, a family of engineered wood products: cross-laminated timber, laminated veneer lumber, glued laminated timber, that are manufactured by bonding multiple layers of wood together under pressure to produce structural elements of considerable size and strength. The use of mass timber in tall buildings is not, strictly speaking, new. Heavy timber construction has been used in industrial and commercial buildings for more than a century. What is new is the engineering ambition of recent mass timber projects and the regulatory evolution that has begun to accommodate them. Buildings of 8, 10, 12, and in a handful of cases 18 or more stories have been constructed using mass timber as the primary structural material in Scandinavia, the United Kingdom, Canada, Australia, and the United States. The Brock Commons Tallwood House at the University of British Columbia in Vancouver, completed in 2017, is an 18-story student residence that used a hybrid structural system of mass timber floor panels supported on timber columns with a concrete core providing lateral stability. At the time of its completion, it was the tallest mass timber building in the world. It has since been surpassed by several projects in Norway and other countries where mass timber construction has a longer regulatory history. The engineering arguments for mass timber in tall buildings are several. Wood is a renewable material. A timber building can, in principle, be supplied from forests that are managed sustainably, with the carbon stored in the wood representing a reduction in atmospheric carbon dioxide that persists for the life of the building. The manufacturing of mass timber products produces substantially less embodied carbon than the equivalent quantity of concrete or steel, which require energy-intensive industrial processes involving very high temperatures. For developers and building owners increasingly subject to pressure to demonstrate carbon responsibility, mass timber offers a material story that concrete and steel cannot match. The engineering challenges of mass timber in tall buildings are also several. Wood is combustible. This is its most obvious practical disadvantage in a building type where fire resistance is paramount. The response of the mass timber engineering community to this challenge has been to demonstrate, through testing and analysis, that large timber members exposed to fire form a protective char layer on their surface that slows the progression of burning into the interior of the member, and that properly designed mass timber structures can achieve fire resistance ratings comparable to those required for concrete and steel structures. Building codes in most jurisdictions now have pathways that permit mass timber in buildings up to 18 stories, with specific requirements for the management of exposed wood surfaces, sprinkler systems, and char-based fire resistance calculations. Connection design in mass timber structures is a specialized engineering challenge because the material properties of wood, its anisotropy, its variability, its sensitivity to moisture content changes, its creep behavior under sustained load, require connection details that differ substantially from those used in steel or concrete construction. The specialty engineering firms that have developed expertise in mass timber connection design are in considerable demand as interest in the building type grows. The acoustic performance of mass timber floor systems is another area requiring careful engineering attention. Mass timber floors tend to be lighter than concrete slabs of comparable structural span, and lighter floors transmit impact noise, footsteps, dropped objects, more readily than heavier ones. Managing impact sound transmission in a mass timber building requires careful attention to floor assembly detailing, and sometimes additional acoustic topping layers that add mass and damping. Whether mass timber ultimately proves capable of reaching the heights of conventional tall buildings, the 200, 500, 1,000-foot territory of steel and concrete super talls, remains an open question. The structural engineering community is actively researching this boundary, and there is no shortage of ambition in the proposals being developed. Buildings of 30, 40, 50 stories in mass timber have been seriously proposed and, in some cases, are under development. The engineering is solvable, in principle. Whether the regulatory frameworks, the insurance markets, and the cultural confidence in the material will develop quickly enough to support these ambitions is harder to predict. Seismic engineering and the cities. The story of tall buildings cannot be told completely without addressing the ground that moves. Earthquakes are one of the most fundamental constraints on tall building design in a significant portion of the world's major cities. Tokyo, Los Angeles, San Francisco, Istanbul, Tehran, Mexico City, Taipei, Christchurch, and dozens of other cities where tall buildings exist or are being built sit in seismically active regions where ground shaking is not a theoretical possibility, but a periodic reality. The engineering of tall buildings for seismic resistance is a specialized discipline that has evolved dramatically over the past century, driven both by advances in understanding of earthquake ground motion and structural response, and by the hard lessons of actual earthquakes. The fundamental challenge of seismic design is different from the challenge of wind design in ways that are not always obvious. Wind loads are essentially static or slowly varying. The wind pushes on the building, and the building must be strong and stiff enough to resist. Seismic loads are dynamic. The ground moves, and the building's response depends on the interaction between the ground motion and the building's own dynamic characteristics, particularly its natural period of vibration. A tall, flexible building has a long natural period. It sways slowly in response to dynamic forces. A short, stiff building has a short period. It snaps back and forth quickly. Earthquake ground motions contain energy at a range of frequencies, and a building whose natural period coincides with the dominant period of the ground motion it experiences will respond with amplified oscillations. The resonance problem again, but now driven by the ground rather than the wind. Seismic design codes specify the forces that buildings must be designed to resist based on the seismic hazard at the site, the building's height and structural system, and the importance of the building's function. But modern seismic engineering has moved well beyond simply designing buildings to be strong enough to resist specified forces. Performance-based seismic engineering, a framework that explicitly considers how the building is expected to behave across a range of earthquake intensities, from the frequent small earthquakes that should produce no damage to the rare large earthquakes that the building should survive without collapse, even if some damage occurs, has become the standard of practice for significant tall buildings in seismically active regions. The structural systems used to provide seismic resistance in tall buildings include many of the same elements used for wind resistance: stiff cores, moment frames, braced frames, but also some systems specifically developed for seismic applications. Base isolation, for instance, involves mounting the entire building on a system of specially engineered bearings, lead rubber bearings, friction pendulum bearings, that decouple the building's motion from the ground motion during an earthquake. The building, instead of being rigidly connected to the shaking ground, sits on bearings that absorb and redistribute the seismic energy, significantly reducing the forces transmitted to the structure above. Base isolation is most effective for relatively stiff, lower-height buildings because it works by lengthening the building's effective natural period, moving it away from the dominant energy content of typical earthquake ground motions. For very tall buildings, whose natural periods are already long, other energy dissipation strategies, supplemental damping devices distributed throughout the structure, energy dissipating connections between structural elements, are more appropriate. Japan's approach to tall building seismic engineering is perhaps the most sophisticated in the world, driven by the country's extraordinary seismic exposure and the engineering culture that has developed in response to it. Japanese tall buildings are routinely subjected to detailed performance assessment for multiple levels of seismic hazard, and the use of supplemental damping devices, viscous dampers, hysteretic dampers, buckling restrained braces, is far more common in Japanese practice than in most other countries. The 2011 Tohoku earthquake, which produced ground shaking that was felt strongly in Tokyo, despite the epicenter being several hundred miles away, provided a large-scale real-world test of the seismic performance of Tokyo's tall building stock, a test that was, on the whole, passed with considerable success, though not without observations that informed subsequent improvements in practice. The super tall and the mega tall height records in skyscraper construction are a curious phenomenon. They are pursued with an intentionality that is rarely purely functional. No developer builds the world's tallest building simply because that height is required by the program. Height records are pursued for reasons of prestige, marketing, national pride, urban ambition, and occasionally the simple human desire to do something that has not been done before. The structural and engineering communities tend to regard pure height records with a mixture of professional interest and mild skepticism. The engineering challenges are real and interesting, but the functional justification for extreme height is often less compelling than the promotional materials suggest. The Council on Tall Buildings and Urban Habitat, a Chicago-based organization that maintains the authoritative database of tall building heights and classifications, defines a super tall building as one exceeding 300 meters, approximately 984 feet, and a megatall building as one exceeding 600 meters, approximately 1,969 feet. As of the mid-2020s, there are more than 24 super tall buildings in the world and 3 megatalls, with more under construction or in advanced planning. The Burj Khalifa in Dubai, at 828 meters, remains the world's tallest completed building. It is likely to retain that record for a limited time. The Jeddah Tower in Saudi Arabia, under construction at various points over the past decade and currently anticipated to reach 1 kilometer in height, has been designed to surpass it when complete. Whether the Jeddah Tower will ultimately be finished is a question that remains genuinely open, given the project's history of delays and funding challenges. The history of record-seeking tall building projects includes a number that were conceived ambitiously and completed differently, or not completed at all. The engineering of truly extreme tall buildings, buildings in the 600-meter and above range, encounters challenges that are qualitatively different from those of merely very tall buildings. At these heights, the building extends into wind environments that are significantly more severe than those near the ground. and the aerodynamic behavior of the building becomes an increasingly dominant design driver. The structural systems required are more massive and more expensive per unit of floor area than those of shorter buildings. The elevator systems required to serve extreme heights involve multiple transfer floors and long travel times that affect the building's operational character. The mechanical systems must cope with pressure and temperature differentials that span a significant fraction of a kilometer of vertical distance. These challenges are solvable with current engineering knowledge, as the existing megatall buildings demonstrate, but they are expensive to solve, and the economics of extreme tall buildings are frequently difficult to justify on purely functional grounds. The buildings that have been built to megatall heights in Dubai, Shanghai, and other markets have been supported by specific combinations of land economics, government ambition, and favorable financing conditions that may not be replicable everywhere that developers have proposed such buildings. The future of tall building construction is, in all likelihood, less about records and more about the gradual and unspectacular improvement of tall buildings as functional environments, better integrated systems, lower energy consumption, better acoustic performance, greater structural resilience, more sustainable material choices, and more adaptable interior configurations that can respond to changing patterns of work and habitation. The building types that will matter most in the coming decades are probably not the 1-kilometer tall trophy towers, but the 50 to 100-story commercial and residential buildings that constitute the bulk of the world's tall building stock, and that are being built in large numbers in cities across Asia, the Middle East, and increasingly in other regions as urbanization continues. What the next skyscraper will have to solve. Every generation of tall building construction has confronted a set of engineering problems that seemed, at the time, at the boundary of what was possible. The engineers of the 1880s confronted the problem of building a rigid frame tall enough to be genuinely useful without collapsing under wind. The engineers of the 1960s confronted the problem of building efficiently to 200 stories. The engineers of the early 21st century confronted the problem of building to 600 meters. Each generation solved the problems it faced, and, in doing so, revealed new problems that the next generation would have to address. The problems facing the next generation of tall building engineers are partly technical and partly systemic. The technical problems include the continued development of more efficient structural systems for extreme heights, the improvement of mass timber construction to extend its range, the integration of renewable energy generation into building facades and rooftops in ways that are architecturally acceptable and structurally compatible, and the improvement of building systems to achieve dramatically lower energy consumption without compromising occupant comfort. The systemic problems are arguably more interesting and more difficult. The relationship between tall buildings and the urban infrastructure that supports them, the water mains, the power grids, the transportation networks, is a two-way relationship that is not always well managed.